Okay, so one of the things that you would like to know when you are using batteries or in your when you are using batteries, for example, how long will they survive? Will it last 5 hours, 6 hours, 10 minutes? So in that sense, you might need to know how much current will be running through it. Now, in these simple circuits, like this one, there are just the two resistors connected in series, two of them connected in parallel. It will be kind of trivial to determine how much current runs through it. You just need to calculate the equivalent resistance. Now, let's just complicate the circuits a bit. Well, this will still be a simple problem, in the sense that if you look at this, you have these two resistors connected in parallel, so you can already determine their equivalent resistance. So in a sense, this circuit is the same as this circuit over here. This will be R1 is equal to 1 ohm. What will be the equivalent resistances of these two resistors in parallel? It will again be 1 ohm. It's 1 over 2 plus 1 over 2, which is just 1 over 1 ohm. So this is 1 ohm. So this circuit is also, now we have a circuit with two resistors connected in series. This will still be equivalent to this one. This is our equivalent. This is equal to 2 ohms. So this is the equivalent resistance of my initial circuit. And since we started with 5 volts, I have 2 ohms. The current running through my battery is nothing but 5 volts divided by 2 ohms, which is 2.5 amperes. Now let's go back to the initial circuit. What is the potential difference across R1? It's 2.5 amperes is running over 1 ohm, so it is 2.5 volts, the potential difference between these 2 points. Now, what is the potential difference between these 2 points? Again, what remains? I mean, the potential difference between these 2 points is nothing but the potential difference between these 2 points plus these 2 points. This is already 2.5 volts, so what remains is also 2.5 volts. Now we can talk about the currents running through this one and this one. Well, this resistor has a potential difference of 2.5 volts across its 2 ends, across this resistor. So what is the current running through that one? Well, 2.5 divided by 2, 1.25. So there's the current running through here is 1.25 amperes, and the same over here. This is 1.25 amperes. And again, if you look at over here, the sum of these two currents is nothing but 2.5, which is the total current running through our battery. Now again, this was just kind of an easy circuit. Now let's look at this circuit. Let's say this is R1, this is R2, this is R3. Here you have a battery with EMF V1. Here you have another battery with EMF V2. Now, how can we determine the current running through both of these batteries? Now, we never discussed what happens when we connect a resistor and the battery, in this way at least. No. So what is the current that runs through V1? Or how can we determine it? Now things are getting more complicated. Or let's say we have such a configuration R1, R2, R3, R4, R5. Well, you cannot just simplify it by just replacing series or parallelly connected resistors by their equivalents. We need some more general principle to calculate these ones. And one of you had said we use the Kirchhoffs rules. Now, we already know enough information how to determine these currents. Now, let's stick with the first one. Let's try to analyze this one. Now, what can we say? Let's just first label our unknowns. So I have a current, let's say it comes in this direction. And then at this point, at this leg, I have, let's say, a current I2. At this leg, I have a current I3. I don't know the directions of the currents. Now, I'm more or less sure that this I1 will be in this direction, but for example, this I3, I have no idea, actually, because if you just look at this circuit, this battery will try to push the currents in this direction, and hence in this along these directions, along these paths, but this battery will try to push the current in the opposite direction, on this leg at least. So which one wins? I don't know. I don't really care yet, because currently I'm just setting the positive direction of the currents. Now I will be assuming that I3 will be positive if it is running in this direction. If I3 turns out to be a negative number, it will only tell me that the current is running in the opposite direction. That's the only information I will get. So in a sense, it's like choosing the positive direction in your coordinate axis in mechanics is the same principle. If a current is running in this direction, I will choose it to be a positive current. And if it is running in the opposite direction, I will choose it to be a negative current. What is the potential difference between A and A? It should be 0. But I can also calculate this potential difference by just going around an arbitrary path that starts from A and ends at A. So let's see. The interesting paths for me will be, for example, I can start from here, go along this lower leg, and then come back to the same point. So let me just give some names here. This is B, this is C, this is D, this point, I'm just naming them. And once you get used to these calculations, you don't even need to put these labels. Now VAA is also nothing but VAB plus VBD plus VBC plus VCD plus VDE plus VEA. It should be 0. How many unknowns I have, by the way? We just have 3 unknowns. I don't know the currents. And I'm trying to figure out the currents. So I have 3 unknowns. I need to find 3 equations for these 3 unknowns. Now, this will be one of them. Now, let's see, what is the potential difference between A and B? It is 0. What is the potential difference between B and C? Is it plus or minus? Okay, so in a sense we are calculating the potential. Well, you decided to sum the potential drops. So as I go from B to C, the potential drops by an amount B times I3 times R2. This is the potential drop as I cross the resistor from B to C. Yes. Now you see, these are the total currents running through through my wires. I3 is the total flow of charges in that wire. They will be influenced by this battery over here, this battery over here, all these resistances over there. At the end of all their influences, the current I have in I3 in this wire will be I3. I don't know. I'm just choosing a positive direction. This will be my positive direction. I could have chosen it the other way around, I don't care. If I3 turns out to be a negative current, I will just interpret it as meaning that the current is running in the other direction, not this direction. Okay, now the potential drop across from B to C is I3 times R2. What's the potential drop between C and D? Plus or minus? It is plus. You see, I'm calculating the total potential drop as I go from A to A along this path. From this point to this point, the potential drop is I3 times R2. Now the battery, this long leg usually denotes the higher potential, the short leg denotes the lower potential. So as I go from C to D, the potential drops by V2. You looked so desperate. Okay, is it clear? I mean, that's why I was stressing the fact that you did, by choosing these signs over here, you already decided that you are calculating the potential drops. Okay, the potential drop from C to D is V2. Now from D to E, what is the potential drop? I1 times R3. So you see the current running through this wire is also I1. So the potential drop is I1 times R3. What is the potential drop from E to A? Now it is minus V1, because as we go from E to A, the potential is increasing by V1. An increase in the potential by V1 is nothing but a decrease by minus V1. So since we are calculating the drops, the decreasing potential differences, this is minus V1. So now we have one equation for our three unknowns, 1, 2. The third unknown doesn't appear here. So this is one equation we have. Now, any questions? Well, I mean, just add some more resistance. The basic idea is the same. You can say that, okay, R2 already contains the resistance of this battery, and R3 already contains the resistance of this battery. I mean, the basic principle will be the same. I mean, you can add more resistors, etc. Okay. So what you see, the current, the number of electrons is constant, or number of positive charges. Let's say in 1 second, I'm just making up the numbers. Let's say 5 charges left the 5 positive charges left the battery along this wire. 5 of them split it into 2. Let's just make it up. 2 went up, 3 went down. So 2 charges going in the upper wire, 3 charges are moving in the lower wire. Then when they reach here, they combine and I have 5 charges. I had 5 charges per second. Here I have again 5 charges per second. Now you see here, as your friend had also asked, we are assuming that these currents, I mean, if this is pushing the currents, it will have an effect. Let's compare these cases. Let's ignore this battery for the time being. I will have I1, then I will have I2 and I3 running around these wires, and they will just combine and they will just give me I1. Now I'm adding this battery. What this battery will do is it will push the current in the backward direction in this wire. So what I expect is that this I3 in the presence of this battery should be less than what I would have in the absence of the battery. That is what I would expect. Yeah? I mean, the fact that I1 here and I1 over here is the same is just a statement of charge conservation. If in the previous example I have, let's say, 5 positive units coming here, now there is a battery, so before it was 2 over here, 3 over here, for example, now it will be 4 over here, only 1 over here. 5 arrives, so there should be 5 divided into 2 legs, and when the 2 legs combine, I should still get 5. Well, we will see what happens to these batteries. First, let's write the equations that will tell us how we can determine this I1, I2, and I3, and then we will discuss what happens to this battery. Over here. Well, let's discuss the possibilities later on. Okay, let's first solve it and let's discuss what the various possibilities later on. VAA, the potential. A and B, what is the resistance? They are on the same conductor. Well, if they were on the same conductor, in electrostatics, we would say that they have zero potential difference between A and B. Now, we are not in electrostatics. We have these moving charges. So although, for example, the point B and D, they're on B and C, they're on the same conductor, there's still some potential difference, and that potential difference will be parameterized by a resistance. If there is no resistance on a conductor, then there is no potential difference, although the currents are flowing. If there is a resistance, if there is a potential difference on a conductor that carries a current, then we say that there is a resistance. Now, any questions on how we write this equation? Well, let's see. Now, the batteries, the long legs are the positive terminals and the short legs are the negative ones. Now, the positive terminal of a battery is at a higher potential than a negative terminal. So what we are doing over here is we are calculating the potential difference between the point A and point A, which is obviously 0. Now, we can calculate that potential difference along this path. So let me also draw my path. We are considering this path. Now, as I'm moving along this path, here I am at a higher potential region, and here I am at a lower potential region. So there's a potential drop. I'm at a high potential, I mean, you can think of this as a hill. I'm at a higher potential region, then I go down. Now, it depends on my path, in fact. Well, it depends on how I connected it. I have no mention of the current. The battery always keeps the positive terminal at the higher potential than the negative terminal. I don't really know about the direction of I3. The potential drop across a resistor depends on the direction of the current. Well, let's see what would have happened if we had chosen the direction of the currents in the opposite sense. Let us choose both of these in that direction. Well, choose them in, I'm not really choosing the direction of the currents, I'm choosing the positive sense of the currents. And let's write again VAA. We said that this was VAB plus VBC plus VCD plus VDE plus VEA. Again, VAA, the potential difference between A and B, since there is no resistance in between, it is 0. Now, what is VBC? The potential drop from this point to the other point. It will be minus I3 times R2. Now, why minus? Because I chose the positive sense of the current to be from right to left, while the current flows from a high potential to a low potential. So this point C has a higher potential than point B. So the potential drop as we go from B to C is minus I3 times R2. At the end of the calculation, of course, the current might actually be running in the opposite direction. But that would tell me I3 is a negative number, so the potential drop from B to C would be positive. But this term, if I3 is negative, is positive. Now, as I go from C to D, what is the potential drop? As I go from C to D, what is the potential drop? No, it is plus V2. It is still plus V2. The potential drop across a battery has nothing to do with the direction of the current. It's a property of the battery that the battery always keeps the positive terminal at a higher potential than the negative terminal. That is what the battery does. Yeah. You can describe it in various means. The positive terminal is always at a higher potential than the negative terminal, independent of the direction of the current running through the battery. No? Okay, what about D and E? The potential drop as we go from D to E? Now you see, I1, the positive direction of I1 is in this sense from D to E. Those are my positive directions. It just tells me that your observation is telling me that at least one of these currents should be negative. But still, I can choose these positive directions. No problem with that. Okay, from D to E, what is the potential drop? I1 times R3. What is the potential drop as we go from E to A? Now, I am going from a lower potential to a higher potential. The potential is increasing. So the potential drop is minus V1. Now, if you would compare these two equations, by the way, both of these equations are correct. If you compare these two equations, the difference is this sign over here. But that is to be expected because in these two different conventions, we only change the directions of I3 and I2. Now, I3 is positive in this convention. I3 is positive if it goes in the opposite direction to the previous convention. So I3 changes sign. We didn't do anything to I1 or anything to the batteries. So these two equations are still the same equation with different conventions. If this equation would lead me to a positive I3, this equation would lead me to a negative I3. But since the positive direction in these two equations are different, they will still represent the same current. Okay, we still need two more equations for our three unknowns. They should. The same in this sense. One of them, let's say, if this equation plus the other two equations we write tell me that I3 is 1 ampere, this equation and the remaining two equations will tell me that I3 is minus 1 ampere. But minus 1 ampere here will mean that the current will be running from the point B to C. And in this example, plus 1 ampere will mean that the current is running from B to C. Both of them will give me the same direction of the current and the same magnitude of the current. Because these directions are just my choices. They are completely arbitrary. I mean, I would stick with this one. And for this case, it's kind of obvious the direction of I1, the direction of I2. Well, the direction of I3 is kind of vague. We don't really know yet. And it will, in fact, depend on the values of V1 and V2. But even if it's not obvious, you can just choose any one you like. You don't need to worry. You don't waste too much time on which directions to choose. They will eventually give you the same result. Now let's write the other equations. Now let me... So let's say we called A, B, C, D, and E. Let me also put another point over here. F and G. So again, VAA. Now we already had found one equation by starting from this point A, going around my circuit through the lower wires, and then back to the point A. Now I can consider starting from A, I can go around the upper wire and go back to A. Then the potential drop as I go from A to A, which will again be 0. It is VAF plus VFG plus VGE plus VEA. Now, what is VAF? That's again 0. What about FG? The potential drop is I2R1. What about GE? I1R3. And EA is again minus V1 because the potential as we go from E to A is increasing. If we look at the connections of the battery, So the potential drop is minus V1. Okay, this is our second equation. This was the first equation in terms of our unknowns. This is our second equation. Now we need a third equation. Now let's look at this point. I1 is carrying a current at that point. I2 and I3 are carrying currents away from that point. Now, whatever charge arrives at this point, it should leave that point. There is no accumulation of charges anywhere. I mean, the charges are accumulated only at capacitors. There is no capacitor here, so there is no accumulation of charge. So whatever charge reaches this point, it should leave. So that tells me that I1 should be equal to I2 plus I3. This is my third equation. Now I have 3 unknowns and 3 equations. In principle, I should be able to solve them. Well, which way? I mean, the only thing is you have to go along a continuous path. So, for example, I can imagine such a path. I can start from here, go like this, make one turn, make another turn, and come back. This is a valid path. Or I can just start from here, from point A, the only important thing is that you have to go along a continuous path. I mean, you cannot just, let's say, start from here, go to over here, start from here, go here, and then start here and go here. No. It has to be a continuous path. Just imagine you are taking one positive charge and moving it around. It doesn't jump from point to point. It just moves smoothly. Well, you can, if you want to. It should still give you the same point, because what we are actually doing is calculating the potential difference between A and A. And the potential difference between any 2 points, even if those 2 points are the same, is independent of how you start from the initial point and how you reach the final point. You can choose an arbitrary path. You don't have to follow these conductors. But the problem would be if you are not following the conductors, how can you obtain the potential differences? I mean, if you are following a conductor, if you know the current, if you know the resistance, you know the potential difference already. But if you, let's say, would like to go around such a path, you should first calculate what is the electric field along that path to obtain the potential difference. I mean, it will be harder, but you can. Now let's go to the other convention, the alternative choice. Now, we said, okay, this was the point F, this was the point G. We already have equation 1. Let's call it 1 prime. Now we can obtain the second equation, which is equal to 0, which is VAF plus VFG plus VGE plus VEA. Now what is VAF? It is 0, there is no resistance across that wire. What about F and G? The potential drop. It is minus I2 times R1. It is minus because the current runs from the positive higher potential to a lower potential. We chose the positive direction of the current to be in this direction. So if there is a positive current, G has a higher potential than F. So if I2 is positive, the potential drop should be minus I2 times R1. This also takes into account the case when I2 can be negative. Okay, plus the potential difference between G and E, potential drop, I1 times R3. The potential drop as we go from E to A, minus V1. This is the equation 2 prime. And our third equation, again, you can just take any point that you like. Let's just take this point, again, that will give me another equation. The currents that are carrying charges at this point are I1, I2, and I3. So the total charges reaching that point is this one. The charges leaving that point is 0. So the sum of these three charges should be 0. This already tells me that at least one of these charges should be negative. That is, at least one of these charges are pointing in the other direction. This should be satisfied. Now, do you agree with this equation? So this tells me that not all three can be positive, and not all three can be negative. At least one of them is positive, one of them is negative. So that tells me that at least one of the charges, one of the currents, is not running in this positive sense, but it is running in the negative sense, in the other direction. At least one. Which one? I don't know. Because the sum of these three should be 0. Charge conservation at this point, because if all of them are positive, that means all of these currents are carrying positive charges right at that point, at the intersection. So I would end up having an accumulation of charges at that point. But I don't have any accumulation anywhere. No, not in this one. Not with these conventions, no. You see, for every circuit, you first choose your positive senses, just like in mechanics, you first choose your positive directions. And then you write equations based on your choices. Now, in the previous case, this was our choice. I2 and I3 were taking charges away from positive I2 and positive I3 meant that they were taking charges away from this point. So I1 was bringing charges into this point, and I2 and I3 are taking them away. So whatever is brought by I1 should be taken away by I2 and I3. But in this convention, if I1 is positive, I2 is positive, I3 is positive, they are all carrying charges to this point. So the amount of charges accumulating at this point per unit time is just this, the sum, I1 plus I2 plus I3. But we already, in these systems, we are studying systems in which the only place where charges can accumulate are capacitors. So there's no capacitor here. You cannot have any charge accumulation anywhere. So the accumulated charge at this point should be 0. Well, for example, we can discuss certain limits. Let's imagine that R1 is infinitely large. Okay, that's one limit we have. Now, if R1 is infinitely large, then I2 should be 0. There shouldn't be any current running through it. So I2 is 0. That means I1 and I3, I only have currents along these two batteries. Now the battery V2 is trying to carry my charges in the counterclockwise sense, whereas V1 is trying to carry the current in the clockwise sense. So if we say, okay, R1 is infinite, V2 is larger than V1, then I would have I3 positive, I1 negative. So this is one of the limits where we can say something about the signs. So let me just take this one. Let's say R1 is infinite. Now, if V2 is larger than V1, then we would expect I3 to be positive, I1 to be negative. If V1 is less than V2, then I3 will be negative and I1 will be positive. For example, this is one limit where we can say something about the signs without solving our equations. Or we can say, let's imagine R2 is infinite. And since R1 is infinite, we can also say I2 is equal to 0. Now, if R2 is infinite, then we know that I3 is equal to 0. R2 is infinite, so there cannot be any current passing through this wire. Now, in this case, let's say I1 will be positive and I2 will be negative. In fact, I1 will be equal to minus I2, which will be positive. And we can even tell what it is. I1 will be nothing but V1 divided by R1 plus R3. Why? Because in that case, if R2 is infinite, just forget about this wire. We have one battery connected to two resistors which are connected in series. Their equivalent resistance is R1 plus R3. The equivalent resistance is R1 plus R3. The potential difference is V1, so the current that will be running through my system is V1 over R1 plus R3. Now in these limits I can say that I can talk about the exact result should be these ones, I already know them. Their signs can be different. Now if now V2 is larger than, smaller than V1. Well, let's give a break here. Have a break, and after the break we will continue discussing.